Welcome to Differential Equations, Section 5.1. In this chapter, we're going to start to look at systems of differential equations. And in this section particularly, our first look is some things about matrices. Some of it you might know already, some of it might be new. And then we're going to see how to apply that to some systems of differential equations. So here in question 1, we are given matrix A, matrix B, and we want to do some operations. So we've got 5A plus 6B. So 5 times A, that's just multiply everything in the matrix by the constant 5. And B, here's matrix B, multiply everything in there term by 6. And so now if I want to add these two things together, I simply add them in the particular place it's in. So 40 plus 12 minus 10 plus a minus 24 and so on. And so this is the result of 5a plus 6b. In part B here, we have 6a minus 5b. All right, so take matrix A again, multiply through by 6, take 5 times b. Now we're going to subtract element by element. So 48 minus 10. Minus 12 minus a minus 20. So minus 12 plus 20, which is a positive 8. All right, continuing on, we next look at A multiplied by B. When you multiply two matrices together, you have to first see, is it defined or not? So looking here at matrix A is 2 rows, 2 columns. B, 2 rows, 2 columns. Now the important thing to look at is if you look at the number of columns of the first, does it match the number of rows of the second? If that matches, then the multiplication is possible. And if you look at the outside two numbers, that says the size of your answer. So how do you multiply? Well, you take the rows of your first multiplied by the columns of your second. So I've got 8 times 2 is 16. Now I'm going to add minus 2 times 5. So I get a minus 10, so 16 minus 10, which is 6. Now to get this position, I'm going to take the first row times the second column. And so I get 8 times minus 4, so a minus 32. A minus 2 times 1, so a minus 2, and so on. Another way to think of it is when you look at the answer, this is C11, C12, C21, C22. And if you look at these indices, it tells you that to get this item, I'm going to take the second row of the first multiplied by the first column of the second. And so here is A, B. Then they want you to do B times A. So we are reversing the order. Now certainly with normal numbers, 2 times 3 equals 3 times 2. It is commutative. With matrices, that's not often the case. So 2 times 8 is 16. 2 minus 4 times 4 is a minus 16. So this row, this column. And so we get this answer for B times A. And if you compare these two, I'm looking at AB and I'm looking at BA, and they are not the same. All right, in question 2 here, we're given an A, a B, an X, and a Y. So they want me to find a Y. So is it possible? Well, A has 2 rows, 3 columns, so 2 by 3. Let's see Y. Y has 1, 2, 3 rows, 1 column. So yes, see these numbers match. And so the answer will be 2 by 1. So take the first row times the first column. And so this is what we get. Second row times this column, and that's what we get. You see my answer here, this is C1, 1. This is C2, 1. So again, the indices tell you what gets multiplied. All right, what about A times X? All right, well, A is 2 by 3, and if you look back up at X, it's 2 by 1. No match, and so this multiplication is not defined. B times X, let's see, 3 times 2, and this is 2 by 1. Insides do match, and so the answer will be 3 by 1. So first row, first column. Second row, first column. Third row, first column. And BY, the sizes don't work out, so it's not defined. All right, in question 3 here, let's see, we have matrix A1, A2, and they want me to form the subtraction. Well, subtraction, again, I didn't mention this before, but when you add and subtract matrices, they must be exactly the same size. So yes, they are here, 2 minus 1, 1, and so on. If I find the determinant of A, my answer here, what do? It's the downward diagonal, that product, minus the upper diagonal product, and that's 0. They're giving me matrix B here, and they want me to find the determinant, so 12 minus 12 is also 0. So here's the determinant of A, here's the determinant of B. They now want me to form A multiplied by B. So here's A, here's B. The sizes work out. First row, first column, and I get this stuff. And then first row, second column, so 1 times 3. 1 times 3 is 3, minus 1 is 2. So minus 1 times 12, add 4, minus 8, and so on. And so they say, well, what is the determinant of this new matrix A times B? Let's see, 8 times minus 2, this would be a minus 16 minus, and minus 8 times 2, the other diagonal. So I got minus a minus 16, and so when I add that up, I get 0. And what they wanted you to notice is that the determinant of the product is the product of the determinant for each of them separately. Let's see, question 4, they want me to write this system of differential equations in the form x prime equals p of t times x plus f of t. All right, well, looking at this, I don't see any t's in there, so I'm just going to rewrite this. The x is missing. All right, and on the second one, the y is missing. And so when I form matrix A, it's just the coefficients in front of the x's and the y's. All right, they want me to do the same thing here. So let's see. I've got y and a z. X is missing. I've got an x, no y, but a z. An x, a y, and a z. All right, so to form matrix A, I simply grab off all those coefficients. All right, in question 6 here, we want to verify that the things that they gave us are solutions, and we want to use the Wronskian to make sure they are linearly independent. All right, so let's see. Here is matrix A. Here's x. x1 is e to the 13t times this column vector. And so if I actually multiply this out, here's x1. So, and what is x1 prime? So that's just find the derivative for each piece. So save that. So now let's see if it's true that x1 prime actually is a times x1. So here's a, there's a. Here it is x1. The multiplication makes sense because the inside parts do match. So let's see, first row, first column. I'd have 17 times 3, which is 51, minus 12, and they both have this e to the 13t. Then I've got 20 times it, so 60, minus 17 times 2. And so when I simplify this, this is what I got for AX1. And yes, that does match x1 prime. So yes, it is a solution and it does work. Then they want me to repeat this for x2. So basically no change, just grind through it. And then notice that yes, it does work. All right, so my general solution is going to be C1, X1, C2, X2. And so if I put those constants in front of my solutions, my general solution is a matrix, and it looks like that solution. So let's verify with the Wronskian. So now I'm going to take all of this stuff, find the Wronskian, so it's the downward diagonal minus the upward diagonal product. Well, the good news is the e to the 13t multiplied by e to the minus 13t. The exponents add and you get e to the 0. Same thing happens there. So all you have left is 5 times 3 is 15 and a 2. And so you see the Wronskian is a constant 13. It's never 0. So the two solutions are linearly independent. All right, in question 7, they want me to find a particular solution. So what are they giving me? Well, first they're giving me the system. So we could write all this out for what that looks like for x1 and x2. But they're telling me that the answers look like the following. So I've got x1 and x2. They are now giving me some initial conditions. All right, so my general solution is C1 times the first, C2 times the second, which looks like this for x1 and x2. So if I plug in what's going on at 0 for both of them, so let's see. If I plug in 0 here into x1, I get C1 plus C2, that must be 4. And for x2, if I plug in 0, I get minus 4, C1 plus 5, C2. So I've got a system of two equations and two unknowns. I see I can simply multiply by a negative 1 and the C1s would cancel. I get 4C2 is minus 8 and I get C2 is minus 2. Plug that into the top one and I get C1 is 6. And so my basic answer looks like that. And that's all we have for this section. Next section, we start to look at eigenvalues and eigenvectors.